Pulmonary arteries are going away from the heart to the lung. I'll move this back one on.
Thanks.
There we go. So, is the blue one up there an artery or a vein?
Okay.
I mean, your gut reaction would be, say, vein, because it's blue. This is pulmonary circulation. It's kind of like the ductus arteriosus, foraminal valley, and ductus venosus that you see in a baby in the circulatory pattern. That is, blood is coming out to the lungs to pick up oxygen. So it's coming from your body, but it's coming from your heart. So that blue vessel there is a pulmonary artery. And the red vessel going back has now picked up oxygen. So it's going back toward the heart, to the left-hand side of the heart. So don't be confused. The capillaries that are sitting there are all interrelated, lacework-looking kind of sections. But the blue part is arterial and the red part is venal. This is a term we haven't used before, I don't think. It came up this morning in lab. It's called an anastomosis. An anastomosis is one of these networks that looks like this around the outside, like a ball of capillaries. And it could allow some blood to remain at nearby a capillary for a period of time. It could go around in a circle a couple times instead of just going in and then right back out. Consequently, it includes and increases the surface area as well as the residence time of the blood going through the capillaries at an alveolus, so you can get more oxygen in. Now, it turns out that most of the exchange of gases in the alveolus and at the alveolar wall is done by diffusion. 99% of it essentially is diffusion. So it only goes from a high concentration of CO2 to a low concentration. Consequently, high oxygen concentration goes to a low concentration. It's just diffusion, and the two gases go back and forth. In the respiratory system, aligned with the circulatory system, red blood cells actually carry about 70-72% of the CO2 as well as the oxygen. Not in hemoglobin, it's just dissolved in the plasma on the inside of the cytoplasm, on the inside of the red blood cell. Why isn't a red blood cell really a cell, by the way? What's it lack that most cells have? Nucleus. It doesn't have a nucleus. So here's the alveolar organization. If there's a better view of it with a scanning electron microscope view of alveoli and alveolar sacs and alveolar ducts. So, as we'll see in the following overheads, alveolar ducts come off of respiratory bronchioles. Respiratory bronchioles are the thinnest little part of the tree that leads to the business end of the respiratory system. But it's kind of like the circulatory system in the sense that the heart and the bigger vessels are simply the delivery system. That's not where the action is. The action is at the thin membranes of the capillaries that are right next to the wall of alveoli. If you found a blood vessel, I don't see one here. This might be a blood vessel, even though they have labeled as an alveolus. There might be a blood vessel there, and that might be one right there. The wall of the blood vessel and the wall of the alveolus together, both of them together, could be less than 0.5 of a micron. So that's 1/15 roughly of the size of an RBC. It's really thin. Consequently, it's pretty easy to build up fluid in the lungs. It's not difficult to damage the lungs because they're such thin tissue. The alveolar duct branches off of the bronchioles, and that becomes an alveolar sac. So this whole thing is an alveolar sac. And then individual alveoli stick off of the alveolar sac. It's kind of like if you worked in direction, you have a whole big bunch of grapes, and you trace back from the stem to the grapes. There'd be some side branches and some smaller side branches, and eventually one little branch went out to one little grape. And that's where this is. The alveolar sac has maybe 6, 8, 10 alveoli sticking off the surface. You might want to add to your list, if you're keeping a list, I hope you are, of the miraculous packaging units in the body. You know, just big numbers, small numbers, packaging wondrous things. And one of them happens to be the alveoli, the number of alveoli in both sides of the lungs. If you count the right and the left, it's a lot. I won't give it away because it's in the reading. I'll get you to read it. But it's 300 and something million. I'll give you that much. It's a large number. There are lots and lots of alveoli. As a consequence of the section, there's the diagram that I was alluding to. Here's a section from, here's a red blood cell, and here's a capillary. Here's the lumen of the space in the capillary, and here's the endothelium. Remember, that's about all they have. And here's the alveolus on this side where the airspace is actually sort of outside the body. It's down inside your lungs, but it's actually outside the body. And the alveolar epithelium and these two together could be as low as half a micron. It's really thin. It can get torn up, it can get parasitized, it can get inflamed, it can be infected rather easily. What do you call the outside of the lung? Let me turn the light on for a minute. What do you call the outside of this structure? If it goes over an organ, then it's called visceral or parietal. Other way around. So it's visceral. If it goes over the surface of an organ, there's an organ. In this case, there's a mediastinum that goes down the middle, and you can see where the diaphragm sits right here, curved over. And that hole right there, going through the other way, is where the inferior vena cava goes through. So it sits, the diaphragm sits like this, and the inferior vena cava goes through the diaphragm, the muscle, and goes through that little hole and keeps on going on up. Think it's a human or no? Humans have 1, 2, 3 lobes on the right-hand side, and 1, 2 lobes on the left-hand side. But this one has a third one on the other side. Think it's human? No. What do you think it is? It's a dog. 135 pound German Shepherd. It died anyway, so we got the lungs out. But it's plastic. Remember the hand is made out of plastic, but it actually started out as a real cadaver tissue? So is this. I think the guy there at Davis gave it to me because he figured it was going to get eaten some more. I don't know why the mice were eating this, because it's made out of plastic now, but mice were eating the side of it. And he said, you know, it's not a very good specimen anymore. You want it? And I said, of course I do. It's probably worth a couple $1,000 just to build it. What's this part? With rings of carbon.
Trachea.
So, if this is the visceral coat, this could be the visceral peritoneum. And on the outside of the wall, where this sits inside of the pleural cavities on either side, what do you call that? If this is visceral, then the wall must be coated with parietal. But we don't really usually call it visceral or parietal peritoneum. We usually call it pleura. There's visceral pleura and parietal pleura. And what do you think pleurisy is, by the way? Infection of the outside coat? Does air go through here? Or does air go down the trachea, branches, bronchi, bronchioles, etc., down into alveoli, and then come back out? Air doesn't go through here. The way the oxygen gets to the rest of the body is determined by how many capillaries are involved. So in order to have a reasonably good circulatory system, you have to have a pretty good respiratory system, or you could explain it just the other way. In order for the respiratory system to function, you need a high-powered, enclosed, high-pressure circulatory system to push all of the stuff around. Anyway, you're welcome to handle it. It's nothing dangerous. I usually keep it in this insect tank just so it airs out a little bit. Now I'm turning the lights on. So all of that's done by diffusion, and yet it operates very effectively. You exchange quite a bit of oxygen and quite a bit of air in general, just oxygen, all the time. Here is, from the old book, a section through, a diagrammatic section through an alveolus. There are some kinds of cells, let's see if I can put all the labels up first. What are sometimes called type 1 pneumatocytes, or pneumocytes. Those are these flat cells like this, these really flat cells, not the yellow ones, but these other sections with nuclei in between. Those are called type 1 cells. Type 1 cells are so flat, and they have such little cytoplasm, that it's easy for gases to diffuse through them. So those are the real active cells. In order for them to work, however, there have to be other cells like these. These are called surfactant cells, or sometimes they're called septal cells. And more importantly, just as easily, you can call them type 2 cells, Roman numeral 2, if you forgot. I keep forgetting the tongue in the back of your head, so I'll put more numbers into it. So the type 2 cells are actually much more voluminous. They have a lot more cytoplasm. Septal cells, type 2 cells, surfactant cells, because they secrete surfactant. Surfactant is a lipoprotein that is involved in keeping the alveoli open. So you already knew how this worked, probably, you just didn't know why. Here is an olive ball, like my hands together like that. Olive ball. If I get the walls that are coated with water or with plasma tissue on the inside, if I get them close enough together, the water molecules pull against them, just like a magnet. That's called cohesion. and the cohesion will pull the alveoli closed. If you don't get them too close, they'll stand open. They'll stand open even more and cutting down on the cohesion coefficient if you secrete this lipoprotein to the inside, surfactant, and that keeps them from collapsing on themselves. If you've been lucky enough to never fall or get punched or something else and have all the air knocked out of you, good. But most of us have either fallen out of a tree or done something where you go, you can't get a breath for a while. And that's partly because the alveoli have closed down on themselves and they're sticking together. If you didn't produce an appropriate amount or type or both of the surfactant, it could be that the alveoli would collapse on themselves, no longer be hollow. And in order to take a breath, because this is now thick, in order to get a breath to diffuse across, you'd have to breathe in and then breathe in again to fill up the alveoli in order to pass. It would be really hard to survive if you didn't have surfactant being secreted by these second cells. Now it turns out that one of the diseases in hyaline membrane disease, that is the disease that affects the lungs if the baby is born premature, and we're talking about briefly in lecture today. If you're born prematurely, even if the lungs are fully developed, it could be that the cells are not producing enough surfactant, or a different kind of surfactant, and especially with babies because they're dealing with cartilage rather than bone for ribs and other parts. They actually have collapsed lungs and can die pretty readily. They have an inappropriate amount. There's a genetic disease that does that, and you can actually use artificial surfactant to keep them alive until the regular surfactant kicks in. So there's a third cell as well, a third type of cells. Here is a macrophage. Here's another macrophage, alveolar macrophages. For whatever reasons, they're not called type 3s. It would make life a lot easier if they just had type 1, type 2, and type 3, don't you think? Anyway, they're called macrophages. Sometimes they're called active dust cells. And they phagocytize, they endocytose material that's found in the lungs. So as you breathe in, like right now, you just took in thousands of dust cells and a bunch of dust mites and a lot of skin flakes and probably your neighbor's hair and other tasty things. Well, as you'll see as we get along, those tasty things are usually coughed up in the middle of the night. It's coughed up all the time with me right now because I have the sniffles. Wait, cough drop. Getting down to the nubbins on cough drops. So, most of the respiratory system associated with the circulatory system operates passively, so it's diffusion. But some of it is operated actively. Inside of these cells, inside of these units, rather, inside of this whole unit as an alveolus, are all three of those cells, and they're also capillaries running side by side. So there's an intimate association and connection between circulation and respiration. But you can't have a cell, an alveolus, for example, that's too big because then there's not enough surface area. And it can't be too small because if it is really small, it'll collapse on itself. So there's kind of a minimum maximum size for alveoli, and that happens with all mammals, even with a white whale, a blue whale, or a humpback whale, like I showed you in lecture this morning. The lungs on those animals are about the size of a Volkswagen bus. They're huge. They're just gigantic, way bigger than our shepherd, that kind of guy. So, what would happen if we lay down some kind of disease and it broke down the walls of this alveolar connection? So instead of having, let's say, the volume of a basketball, about this big, to a volume of 6 balloons that fit inside of the basketball, which one of those has the biggest volume? All 6 of these little guys on the inside, or one big one? Or is it a trick question? It is a trick question. It's the same volume, or pretty close to the same volume. But which one has the most surface area? One basketball with nothing on the inside except air, or a basketball filled up with 6 or 7 or 10, whatever, little balloons on the inside? Which, the balloons. So, if you take away the walls between alveoli, you may have the same volume, or pretty close to the same volume, but you don't have the same surface area. And when we measure respiratory quotients and respiratory volumes and all of that, that's only an indirect measurement of what we should measure, but we don't, is the surface area on the inside of the lungs. So if you have a disease called emphysema, where the walls of the alveoli are broken down, you might have a normal amount of lung volume total, but you don't have enough surface area to exchange gases. I'll give you an example that maybe keep you from smoking. Hard to tell. I don't know. It doesn't work for me because I'm the only one that I know of that attacks people on campus if they're smoking. Consequently, I'm going to get my teeth knocked down my throat one of these days because some people are vehement about their right to smoke. It just happened to me like 20 minutes ago. No, 30 minutes ago. Okay. Where the cafe is at the tech building, a lot of people walk out toward the ambulance and they assume that they're off campus when they're there. They're not. They're not off campus unless they're on a sidewalk. So all the signs around campus that say San Jose City College is a smoke-free campus, I did that, along with 3 or 4 other rambunctious students. That was about 5 years ago. We went to the Board of Trustees, we took some surveys, we got some evaluations. We had a straw vote on the faculty, straw vote the students on campus, and it was about 99% against smoking on campus. On the other hand, if you're a smoker, you just say, oh, the heck with that, I'm self-centered, I'm just going to smoke anyway, I don't care what other people think. So, there were a couple of people smoking by the cafe just now while I had a sandwich. I walked over and told them that it was the San Jose City College is a smoke-free campus, would you mind moving off campus? And there's this little word that begins with F. Remember that? I've learned that can be used with students talking to professors pretty often. So they didn't stop smoking, they just went, no, it's something like that. Anyway, so if you smoke, it's possible that one of the 200 different carcinogens, 200 carcinogens in the smoke will break down these walls. And if it breaks down the walls, you don't have enough respiratory surface. You might have the volume, but you don't have the respiratory surface in order to exchange gases. My brother and I adopted a woman, I know it sounds funny, adopted a woman as a grandma. A long time ago. It was a friend of our mother's, and we liked her a lot, and she liked us a lot, so we adopted her as our grandma. We just had an extra one. The last I saw of her, unfortunately, was she was doing this because she smoked 3 packs a day until roughly the day she died. She was in a rest home where this is forbidden with a mask, but she didn't have it draped over her head because the oxygen was sufficient even if she pulled it away for a moment. Because she had to hold it away from her for a moment. She knows what's coming because she was sneaking a cigaboo. So then she'd move away like this, hold the cigarette away, take some oxygen, move away this way. I wished her good luck, and she died a couple days later. After that, probably this is the last time I saw her, from emphysema, or consequences of emphysema. How can I scare you even a little bit more? What's the percentage chance? No, I'll get somebody to quit. I'll help you in any way I can. You need flowers, you need Starbucks, or whatever, just to keep you from smoking, I'll bring it to you. What's the percentage chance that a woman that's Caucasian or Western European or Indonesian, those are the 3 areas that this applies to. What's the percentage chance that a woman between 25 and 35 in those geographic areas or cultural regions within the United States that is diagnosed with small cell lung cancer from smoking will live 5 more years? What do you think? 50%? 55%? 10%? Now you want the bad news? It's 2%. 2% of people that are diagnosed, women that are diagnosed with lung cancer from smoking, that are small cell, da-da-da-da. You know that, 2%. It means there's 98% chance you're going to croak. And kind of miserably, actually. It's no fun getting lung cancer. So you want the good news, guys? What's the percentage chance that a male, 25 to 35, da-da-da-da-da, in the United States will live 5 more years after being diagnosed with small cell cancer? It's a whopping improvement. Because a whole 4% will survive more than 5 years. Whoop-de-doo. Okay, I'll stop there. No, there's one more thing I want to say. So, what's this?
This looks like a kidney.
Kidney? It's a lung.
It's a lung.
It should be black lung, which is actually a miner's disease. You get asbestos fibers and other things, mesothelioma with that. Actually, this is one overhead that was used by students in my physio class. They usually take a week out in the middle of the semester and do presentations on respiratory disease because it's so rampant. It finds its way home culturally as well. So, for example, where are the 10 most air-polluted cities in the world?
Beijing.
Where? China, all 10 of them, as a matter of fact. It used to be that 2 of the cities on the West Coast were included in the top 20, but they aren't anymore. Do you know those 2 cities?
Yeah, when we went to China for the Olympics, they said that the players in the U.S. they found it really hard to breathe.
No kidding. So, Mexico City used to be in the top 10 because it's in a little bowl. Unfortunately, LA is still in the top 20. San Jose is not in the top 20. Aren't you glad?
England.
San Francisco's not even close. That's pretty clear in there. On the other hand, yeah, where is there another place where there's a bowl with a disrupted inversion layer that caps the bowl? So if there's industrial, automotive, or just plain old fire smoke that's being deposited in a confined space, that it's almost dangerous to go outside and breathe. It's the saddest thing. Because I'll give you a clue, even though I can't sing right now. Well, I don't sing well anyway. But name this place. Rocky Mountain High in Colorado. Where's the place? Of all places, it's Denver, Colorado. It's a very air polluted place because it is in a little bowl. Anyway, I just thought I'd throw you in one more shot here about lung cancer. In your study guide, somewhere, there's on the back side of the respiratory quotient, or the respiratory unit, I think, is a listing of diseases associated with smoking. The thing was generated in 1999. I mean, I haven't changed it, but I don't need to change it necessarily. Anybody have it? I'll put it up on the screen. You can find it. I didn't bring my folder. I don't think about it.
Do we have study guide? Yeah, I do.
There it is. Where were you developing this? Can I borrow that? I'll put it up on for people who don't know the guide. So I'll stop doing it, but this is my one shot at it in some cases because I'm not going to get all of it for physiology. These are things from the bottom up that are physiological effects of smoking and secondhand smoke. So some of the ones that I like to tune into because they don't seem like they're very significant unless it hits you is this. Female facial hair or a hairy tongue, which happens more to females than it does to men. So if you smoke and you're a woman, you can have a tongue that has hair all over it. It might be useful for soup and stuff, but I don't think so. And there's all kinds of things. Aneurysms, strokes, SIDS, bad breath, nausea, pancreatic cancer. But I saw this one happen. It was so funny. It was just great. True or false? Vietnamese men smoke at a much higher percentage rate than Vietnamese women.
True.
Oh, yeah. So if you know the Vietnamese culture in Vietnam, every male smokes essentially, just about. And very few females smoke. Well, anyway, there were 3 Vietnamese guys at our old building. They were stooping down as Vietnamese men can do, even when they're older. They bend their knees and they kind of squat on their own legs. And they were sitting there talking and smoking right outside our office. What we weren't happy about, that was before this non-smoking policy went in. It's like 10 years ago. And so Dr. Newton, as if they were sitting right, Dr. Newton walked by and he said, you know, penis cancer is increased by smoking. And he kept on going. He just walked by. And I was behind him because I was in our office back there. It was so funny. These 3 guys instantly got up and they looked at their own pants, you know, where the penis might be. And they went, whoa. And 2 of them ground out their cigarettes instantaneously. The other guy was kind of like dramatic about it. Took one long drag on his cigarette. And then he crushed it out and they walked away. But I think he got them. He neglected to tell them it's only increased by 2%. So penis cancer is like really rare, and it's pretty rare even if you smoke. But it's there, you know, there is a possibility that you had an increase in penis cancer. So if you take a look at this list later on, even if it doesn't keep you from smoking or keep you from ever smoking, you know, you didn't start, maybe you can use it for somebody, you know, that you're trying to keep. Thank you for the one. Trying to keep them from smoking. Hard to tell. Get ready to take a deep breath. You don't have to hold it this time. I just want you to give it a try. Get ready. Get set. Go. Okay, you can let it out. What you just did is inspiration. Not this kind, like you've got a good idea. Inspiration. But inspiration. So here's inspiration. Sternocleidomastoid contracts, lifts up the chest cavity by attaching to the ribs. Then besides that are the scalings. That's not something that you learn. It wasn't on our muscle list. but the scalenes contract and lift up the chest as well. The serratus anterior, you know, attached at least the superior versions of it, attached to the bones. So these guys are taking pictures previously. You don't need to necessarily, because I think it's picture the page. 723. See if I'm right. In the textbook. Something close to that anyway. I think there's a picture of, that's not it? That's not even respiration, is it? No, never mind. So, I thought I was so red hot about this book. I haven't memorized this book yet, but it's coming. Oh, keep going, you're almost there. There, that's the page. So, it's not 723, it's 767. No, 769. That's a similar diagram, side by side, but otherwise. It shows the muscles that are used in respiration. Now, what we talked about briefly in class, in lecture, is that besides the serratus anterior, scalenes, and sternocleidomastoid, the external intercostals between the ribs themselves and the diaphragm all contract roughly at the same time. So they lift up, they lift out, and the diaphragm pulls down and creates a partial pressure. It increases the volume, but that's partial pressure. And that allows you to suck in. In order to breathe out, without doing it forcefully, you just have to relax those muscles. So if you're breathing a tidal volume, regular breath in and out, you would just simply relax those 4 or 5 muscles, and the air would come back out. The chest cavity collapses a little bit, the diaphragm goes back up, and it pushes it out. On the other hand, the other muscles that are involved in expiration, if it's forced expiration, where you're blowing out the candles, or you're whistling or something like that, or vocalization, these other muscles contract in order to blow the air out. The internal, rather than the external, the internal intercostals, the transversus thoracis, that's one we didn't learn. External obliques, the internal obliques, and the rectus abdominis, remember 6-pack or 8-pack, those all contract when you're blowing out the candles. So you should know at least some of the muscles that are involved in sucking in and blowing out forcefully. Ordinarily, you probably blow out between 2,000 and 4,000 cc's, or milliliters, almost same thing, in a single breath. Just depends on how tall you are. It also depends a little bit on your cultural background. Asian women, for example, might have 75% of the expected average for their height for respiratory capacity or vital capacity, and still be quite normal. They just have small lungs. It's just the way it is. On the other hand, as I mentioned in class, big guys like Dr. Newton, he's 6'6", could have 7-liter lungs, and that's a lot of air. I'm not saying he's full of hot air, but I am, so I can say he is. Anyway, you should probably know this part. I'm going to make copies of this one, because it's a little more clear than the other one in the book.
Yes, please.
I think so. I'll try and get it done by Thursday, but if not, we have labs, and maybe we'll get to that eventually. Well, I do want to show you a little bit of this part before I move on. The respiratory tree includes the business end. Here's a lobule down here, and here's a blow-up of it. The trachea, primary, secondary, and secondary sections of the bronchi. Secondary bronchi don't have rings around them. They have little scale-like sections of hyaline cartilage, same cartilage at the tips of ribs and the connection to the sternum. And eventually we get to bronchioles. Now, bronchioles are smaller, a little bit smaller than bronchi, and the bronchioles are primary, secondary, and tertiary. The tertiary ones are less diameters, much smaller cells, and they carry air all the way down to the lobules, which include the alveoli. Now, as you notice, I move this up now. Here are lymphatic vessels. Here is a branch of the pulmonary artery. Remember we said this is blue because it's going to the lungs to pick up oxygen, so it's blue to begin with, even though it's an artery. And here's a pulmonary vein going back to the heart, to the left-hand side to the atrium. Besides that, though, there are other vessels coming to and going from the area of the lungs, and they include lymphatic vessels. Lymphatic vessels, as we'll see when we get there, we're mostly talking about it in lecture, because there's not much to do with it in lab. But the lymphatic vessels are under no cardiac pressure. They're under very low pressure. Consequently, they have to be moved around. Breathing actually pushes fluid through the lymphatics. Part of that is that as blood goes through a capillary bed, it loses volume by losing plasma to the surrounding tissues. it gains it back at the other end. But the lymphatics pick up what doesn't happen by osmosis. Here's what I mean. So here's a vessel. Here it is. There's a vessel. Now it's breaking into small capillaries. And it gets thinner and thinner capillaries. When it gets to fenestrated or continuous capillaries, it's darn thin. And so what little cardiac pressure there is pushes the fluid out into the surrounding tissues. That's what it's supposed to do. The rest of the blood cells, proteins, other things, electrolytes, are still inside the capsule because they're too big to go through the holes and through the walls. When it gets to the venous end of a capillary bed, a lot of the fluid has gone out on one end, but it is left behind the bigger molecules, the proteins, the salts, and other things. As a consequence, this is now hypertonic compared to the outside because the fluid has run out. As a consequence of that, since this is now hypertonic on the inside, it pulls the fluid back in by osmosis. So by the time it gets to the veins going back to the heart, it's almost even up, but it's not quite even up. And what's left over is picked up by these lymphatic vessels. If the lymphatic vessels can't keep up with the load, like if you have the sniffles, like I do right now, so it could build up fluid or build up mucus in your lungs if you're not able to transport it with the lymphatic vessels. So it's an intimate association of the circulatory system, the respiratory system, and the lymphatic system to keep everything in balance for homeostasis. So, questions about this part of the capillary bed? So that's a key concept that we'll explore a little bit more when we get to it.
So, Dr. D,
Yeah.
quick question. So exercise would help move it back?
Mm-hmm. Mm-hmm. Even if you had a cold, moderate exercise would be okay as long as you're not overdoing it. If you overdo it, you become dehydrated, and that makes it worse.
Yeah.
So moderate exercise, even walking, is good. And sitting up, that's one of the reasons sitting up is good. But besides that, let's get to this next part. Why is it that you lay down most of the time when you sleep? Could you fall? If you fell asleep in your chair right now, might you fall out of your chair? Maybe, but you could fall asleep and just be there. True. Possibility, sitting up. Most of the time, there are rational explanations for laying down because you have blood flow that's easier to distribute if it's going sideways rather than up. So your legs do better if you elevate your legs. You might as well lay down your body because your heart is in your upper body anyway. But the other reason is that the lining of the respiratory tract, except for the alveoli, because they can't. If there were cilia in the alveolus, it would be too thick to exchange gases. So what usually happens is if these cilia, here's a photograph of it right there, these cilia paddle along all the time. So from about respiratory, at least the proximal end of respiratory bronchioles and the larger vessels, there's a lining that's paddling along all the time. The cilia are paddling. When you're sitting up or standing up, they're paddling up. But if you lay down, they're paddling sideways. Which one do you think is easier to move things around?
Sideways.
And what usually happens is that all that junk you took in during the day, skin cells, skin mites, hair from your neighbor, and like that, like I was kidding about a while ago, you swallow all of that, and you breathe all of that in, and sometime during the night, as it paddles along with the cilia, getting rid of this junk, it comes up to where the epiglottis is, and you go, and then you go, no, you don't. You usually swallow it. So what you took in with your respiratory system that day, you swallow that night. I raised that partly because with your future human project, it's time's getting close. Not really, but we're only about 7 weeks from the final. Isn't that scary? Anyway, it could be that you design a different system for the respiratory system. Maybe it's not just food that you eat, but it's so dusty and crummy and organic in the future environment that most of what you cough up and swallow during the night is really useful. Maybe it's like a vitamin pill, or maybe it's something that's like 10% of your diet. I don't know. Yeah.
Now, the cilia helps when you're resting for respiratory to filter sideways.
Mm-hmm.
And when you have a patient in congestive heart failure or COPD, and you have them sleep on an incline up,
Yeah.
what is it doing then?
That's different. That's a circulatory system. You're helping the right and the left ventricle too, helping them distribute blood more readily. So it's not the respiratory
So
system.
it's not really for respiratory reasons?
Well, it's so that the fluid doesn't build up in the respiratory system.
Okay.
Yeah. So the lymphatics are involved there.
Okay.
Let me follow on what Yolanda said. It sounds sad to you because it's the first time you've heard of it. I've told this story before, so it's not too painful. Still a little bit. My Uncle Louis, I call him Louis, was in El Camino Hospital about 20 years ago. And he called me on the phone and he said, I know you've been here a couple times this week because he was in respiratory failure. He was in congestive heart failure. And he said, I don't want to live like this anymore. I'm going to die tomorrow. And I said, how do you know you're going to die tomorrow? He said, just trust me. I'd like to see you today. So I went over. We talked about Grandpa and his wife and he said, I'm really glad to have known you. See you later. Maybe see you again some other time, meaning heaven or whatever. Depends on your own view. And all he did was lower his bed. And he died, middle of the night. So it's associated with it, with the fluid buildup. So I still see this kind of smiley face like, I'm committing suicide the easy way. So if I move this over, this is what it looks like at the histological level. One of the cells listed here, are called goblet cells. Goblet cells are single cells that are mucus-secreting glands. They're one of the few glands in the body, like right here. They're one of the few glands in the body that are single cells. There are mucus glands and mucus suborgans that secrete lots of mucus as well, but these are the single ones. Where else do you think? What other systems would involve a bunch of mucus production besides the respiratory system? Digestive system? You have to slide that puppy through, coming out the other end, whatever. And reproductive system, both in males and females. There's production of mucus for all kinds of things. Or movement of sperm cells, all kinds of stuff. And when you look carefully at the surface, these are all cilia on top. If you put your eye up here and look down on it, it looks like someone's shag rug. That's what it says on top there. Shag rug. So it's pretty thick. It looks like a shag rug. And they're paddling all the time. They're not coordinated particularly. They all paddle usually upwards if you're upright. Now you want the bad news or the good news? Good news is if you smoke and you don't smoke too much, your cilia will come back. Now you already know what the bad news is. If you smoke even 3 cigarettes a day, that's considered heavy smoking by the CDC. If you smoke more than 3 cigarettes a day, you usually kill off a bunch of cilia. What are the various structures that are involved in getting rid of the smoke that you're smoked in? What are those structures? The cilia. So the very things that would take care of that junk that you put in your lungs from smoking are bumped off. If you smoke for a long period of time, it'll eventually kill off your cilia and you're not able to get it out. And that's when you wind up with that black lung like I was showing you. At least 2 of our cadavers have black lungs, because at least tars and nicotine on the outside. Okay. We're almost in the bottom. This is kind of for fun. Because it was almost me. That's how I view it. Concord doesn't fly anymore. It's not safe anymore. But what's the percentage of oxygen in atmospheric air?
20%.
20%? 20.9. So like 21%, something like that. What's the percentage of nitrogen?
80.
80 something. So wait, we're already over 100. So it's a little less. It's 79 point something, 78 point something, and about 20 point something for oxygen. If you go to Lake Tahoe, or if you go to Mount Whitney, or if you go to Mount Kilimanjaro in Africa, or if you go all the way to the top of Mount Everest, does the percentage change and does the volume change of oxygen in the atmosphere?
Yes.
Yeah. The absolute available oxygen changes, but the percentage stays the same. So it's about 21%, even if you're on Mount Everest, something like that. Think you could climb Mount Everest without oxygen in the tank? A couple of Sherpas have made it. No non-Sherpa people have ever made it without oxygen, climbing that far. It's 29,000 feet. I climbed Mount Whitney a couple times. I planned to climb Kilimanjaro, but the problem is, remember I showed you the scar from my heart thing? If I get to the top of Kilimanjaro, no helicopter can go that high. It's 20,000 feet. So if I get to the top and I start to croak, I'm going to croak because I can't get you off the mountain. On the other hand, I might try it anyway. You know, the worst places to die than the top of Kilimanjaro. Whatever. Last little bit. inside the trachea. Inside the trachea are these rings. Here's the lumen of the trachea. It has cilia. Here's the esophagus. This is lower than this. So if you poke right there and find something solid, give it a try. Don't hurt yourself, but just try. Is that your trachea? Or is that the esophagus? That's a trachea. But later on, the esophagus goes around to the side, and the esophagus is behind that part. So here's the tracheal cartilage, and as you'll see when you look at the slides of trachea, it's made out of hyaline carbon. All of those scales and rings are made out of hyaline carbon. In addition to that, let's see if I get around that. Oh, there we go. In the chapter, I want you to learn at least the biggest parts of this tracheal mechanism. Here's the hyoid bone. This guy right here. Here's the epiglottis. These are arytenoids. They're actually that are made out of cartilage, made out of hyaline cartilage. And those are connected to the vocal cords down below. So whatever page you have right there, pretty close. Yeah. So on 756, you can see normal as well as inflamed vocal cords. I don't think mine are inflamed, they're just full of mucus. Exactly.